The last session. Our first speaker is Natalia Bochkina from the University of Edinburgh.
Thank you very much for the invitation. It's really great to be here for this and the previous workshop. So my talk is going to be different from most of the talks I've heard the last 3 days. So what we're looking at is conditional dependence graph in Gaussian graphical models, and the problem we consider is the choice of the regularization parameter, and the connection to the networks is that rather than viewing a graph as a graphical model, we look at it as more as a network and try to use network characteristics to select the regularization parameter. I should also say that the work is driven by my PhD student Andrea Cabaya, who is co-supervised by me and Klaus Meyer from BIOS. So this is the outline. I'll give probably most of you know about it, but I'll give a brief introduction to Gaussian graphical models in high dimensions, and then I'll introduce the ways we propose to estimate the hyperparameter of the regularization parameter, and then illustrate performance of the method and compare to others on the simulated data, and then I'll talk, hopefully time permitting, for our motivating data set for gene expression data, and then I'll end with a summary. So this is the notation. So suppose we have n replicates of p variables, which generally will be genes, but could be other. And we assume that they follow normal distribution, and the key sort of object here is the precision matrix omega. Mu is a vector of means, but generally it's relatively simple to estimate. So I'll assume that mean is 0. We have IID copies, and generally this precision matrix represents conditional dependence graph. So effectively, where we have 0, we have conditional independence. And they aim to estimate that graph. So we're not really interested in estimating omega per se, but more whether the entries are 0 or not. And the applications, at least where I come from, is high-dimensional genomic data, where P are certainly genes and N are samples. So typically we have P's of order 10,000, and N probably, if you're lucky, probably of order 100, more likely sort of order of dozens. That's the data. And in that setting, so if P was actually smaller than N, then there is a simple solution. So you can use maximum likelihood estimator, and the omega inverse. Omega is just the inverse of the sample covariance matrix, so it's fine. But if P is large, then it's not. Well, there are many more solutions. The standard assumption is sparsity of some sort. Sort of most of the entries are 0, at least smaller than n squared, in order, p squared. And then usually the ideal penalty one would want to use is, of course, the L0 norm of omega, so the number of non-zero elements, but that's computationally difficult, so usually a convex relaxation of that is used, which is the L1 penalty, sort of generalization of the lasso approach, where this is just the sum of the absolute values. And then for sort of lambda here, which is the penalty parameter, if it's large enough, then this dominates and the estimator is sparse, right? So, and the key problem we're interested in is how to choose that lambda. So at least when we started, that was about 2-3 years ago. I think it's these were the methods. I don't think they've changed very much. So one is just to introduce additional penalty for lambda. So for instance, the standard approach is the information criteria. Another one, sort of the one I wanted to sort of go ahead with, was sort of Bayesian model with a mixture on omega. But when Andrea started working with it, at least for him, it was taking so long to analyze the data that he decided to go for just the point estimate, the G lasso that I presented. However, we sort of preserve the spirit of the Bayesian modeling. I'll tell you about the interpretation of our procedure later on. Other procedure we looked were a two-step procedure for estimating omega. So, for instance, using the G lasso estimator from the L1 penalty, and then choose lambda to minimize some risk function, which is function of lambda and that omega. So for instance, a cross-validation. And there was a work who investigated performance of that method, and they found that, well, both AIC and actually cross-validation, they use k-fold cross-validation, overfits when p is large. It's okay when p is smaller. And then there is a nice method for the stability selection for Meinshausen and Bullman. Don't think they actually choose unique value of lambda. They could have combined the graphs from various values of lambda. So it's not quite the same method, but still it's very good performance. And the sort of closer in spirit to what we were looking for was the stability selection, stability approach to regularization selection. And so that's what we started with. However, it has additional tuning parameter. I'll talk about it a bit later on. So we found that we didn't feel that the problem was actually solved, because depending on that tuning parameter, you can still get, so effectively, whereas instead of choosing lambda, you need to choose that one. And for our method, somehow, for our data, it didn't work. So what we wanted is to get away from sort of looking at omega, because if one look at the L1 penalty, you can see that a small variation, I think from 0.3 to 0.5, so the L1 norm changes smoothly, but the graph topology changes quite a lot. So we wanted to look at network characteristics to use lambda. So that's our way. So, and just a little bit of the notation. So G, I'll call a graph with nodes V and edges E, and A is the adjacency matrix, and in graphical models, it is just the indicator function where the omega is 0 or not. So, the general method we propose is, well, we take the G lasso estimate and then take some risk functional loss function, depending on the interpretation, and then input only the adjacency matrix of this graph there to choose lambda. So that's the key point. And then the next, the rest of the talk is discussing the choice of the risk function. So the network characteristics we looked at was correlation coefficient of the graph. So that's between the nodes. So effectively, is the number number of neighbors shared between nodes I and J, and then just standardized to be between 0 and 1. Effectively, one can look at the similarity measure. Another one is effectively the average shortest path, also known as the mean geodesic distance. And there are many more Drea considered. He probably considered about 10 or something like that. And so the general algorithm here is using a grid of lambdas, fit G lasso estimate, and just choose the lambda, the L, that minimizes the risk or loss function. And in principle, this can be viewed as a point estimator in modularized Bayesian model. So let me just try to explain. So in principle, the G lasso estimator can be viewed as a Bayesian model, right? So we have normal, say, 0 omega inverse, and then we can write, for instance, the elements of omega ij just follow the exponential distribution, I think with parameter lambda, right? So in principle, it is a hierarchical model. Then we have omega, except we also have the adjacency matrix, and I'm running out of, I didn't quite plan the space well. And then we have lambda, let me do it here. So we have y, omega, and then we have the adjacency matrix, and we have the lambda parameter. So lambda influences the choice of both A and omega. And so when we use the risk function based only on the information matrix, in fact, we're just using this part of the model, or effectively, sort of in the standard approach, you kind of use links both ways, but here we effectively cut the link. So effectively, information about the estimates of omega don't influence lambda. I think modularized Bayesian model, that's the terminology of Jim Berger and Susie Bayari in complex computer models. I think David Spiegelhalter was using it early in 2002 or 3, I think, paper. I think they call it cutting edge. So effectively, they were sort of removing the edge here. Anyway, so I think that's the claim of that to be connected to the Bayesian model. So it would be actually interesting to see the penalty we use, how they work formally in the Bayesian model, but I'm not going to talk about that now. So we propose to use 2 risk functions. One is sort of to look at the path connectivity characteristics, so it will be based on the mean geodesic distance. And the other one, sort of, we want to use the cross-validation type approach, but depending not on the precision matrix, but on the adjacency matrix. So let me introduce the first method. So first, just a reminder of this mean geodesic distance. And then what we do is we choose lambda, which corresponds to the largest change in the graph structure. So this is already sort of standardized. So you could, so this is lambda. This is not quite h, but effectively it is. And then you see that if you increase lambda, the sort of the graph becomes sparser, so the distance becomes smaller. And then at some point there is the sharpest jump, and effectively we want to choose the lambda here. We also use not just the difference between them, sort of that, but standardized. So in a sense, we want to penalize for choosing 2 large lambda. So we effectively choose one of the first large jumps. Well, the first relatively large jump. So just to illustrate, for instance, for the true graph that I was showing here, so that one, so there is a simulation. So this is the optimal choice of lambda. So you see there are roughly 2 clusters, whereas this one, just the previous step, see one edge connecting the 2 clusters. So that's sort of our motivation. So I was also curious how lambda compares, for instance, to random graphs. So this is the choice of lambda, sort of smooth density over a random Ederscher graph, and this is for the type of graph I showed you before. Also, we started looking how it connects to the second eigenvalue, so it was of the adjacency matrix, but we haven't quite finished that. There is certainly a connection. The jumps are related, but the actual choice of them, we haven't proved anything yet. So that was the first method, and the second one is that, say we have some risk function. I was using the mean square, of course, can be any power of q if we want. And so if we use some characteristic of a graph, for instance, degrees or shortest paths or something like that, then the standard way is to plug in to change the true value, which is unknown, by some sort of unbiased estimator, so observation or something like that. But for graphs, they're not really easily available. And so what we do is we want to have some sort of original guess. So what we've decided to do is to use the a priori information that the way biologists look at it, they expect that there'll be clusters in the network which are not necessarily independent. So for instance, some genes would behave like hubs, so they talk to a lot of other genes. Some of them might actually talk to a few. And actually what they do in practice, they just do cluster analysis. So what we've decided to do is just choose the best clustering algorithm and use the graph from there as a starting point and see what we can do, what we can improve. And so the network characteristic we started with were, well, actually using our graph correlations. So that's the one I discussed before. And Andrea looked at a lot of clustering algorithms, and he found the one which seemed to do best in estimating global characteristics, for instance, mean geodesic distance, eigenvalues, and things like that. And then the estimator, we call it the, I think, augmented mean square estimator of lambda is simply minimizing the L2 distance between the characteristics in the sort of original estimate and the ones we get from the G Lassler estimate. And the expectation is taken over the sampling, so it's quite an intense, actually, algorithm. Another way, well, let me just say that in principle, if Q equals to 2, it's sum of the mean and variance. And that star estimator I mentioned before, effectively what it says that if we take the variance in this approach, it's just bounded by parameter you set in advance, and you choose lambda for sort of all the graphs with variability within that range. So here, in addition to that variance term, we have a bias term. So that's the difference, squared bias. So if, on the other hand, as we were thinking about the interpretation, maybe a bit more of that measure. So if we look at the order 2 connectivity of the graph, so effectively just look at the correlation we looked at before and just saying whether it's 0 or not, rather than putting a particular value. So in that case, there is a simple interpretation. It's just the expected value of the difference between the true positive and the false positive. So, and then sort of a closer connection to the false discovery rate. I was also curious how close the estimate to the oracle tuning parameter, so when we actually know the truth and take the actual expected value, and sort of different p's and different n's. I don't know if you can see 50, 100, 200, and 500. And these are sort of I think about 60 simulations that we did, and these are the values, the difference of lambda hat minus the oracle, and most of them tend to contain 0. That's the line, except this small n case here. So actually I was glad to see that. So so now I present comparison on the simulated data of these 6 approaches. So this is the mean square error. This is the path connectivity. We have AIC and BIC. This is the stars approach I mentioned. Also, we just use the clustering algorithm to select the graph. So not among all possible clusters, but just among the outputs from the G lasso estimation. So effectively, we do the range of lambda, do clustering, sort of calculate the clustering characteristic, use the Nagnus, and choose the best lambda with the smallest, I think, characteristic, whatever one they use, just to, because as a starting point, we want to see whether this one does any better or not. So these are just the classification of the method. So the penalized likelihood, there are 2 of them, AIC, BIC. The other 4 use network characteristics. They don't quite use the values of omega to select lambda. 2 of them use subsampling, so this segmented MSC and the stars of Liu et al. And they're all fully automatic except for stars, where there is a tuning parameter to choose. Well, this is sort of a complement of subsampling row, really, so the 4 of them are fast. And whether they produce sparse graph estimates, because for gene expression, I think when Adria ran even stars, so he produced this big, fairly dense graph. It's probably relatively sparse, but to interpret it, it was still fairly hard. So our aim is, since it's not really possible to estimate all possible connections, we try to effectively to get the most, sort of maybe fewer, but reliably. So at least that's our goal here, hence this section, whether the estimate is sparse or not. So, and then he did simulated data, he looked at network with hubs and the power law networks. These are the types, and the random networks just for the comparison. These are the types of the network he looked. So he looked at, I think there is also P500, just didn't fit in here, and different ends. So these are the type of networks that he used. So it could be hubs, but which are connected with just one network, could be several hubs. And these are the different power law networks that he was getting. So then what he did is he ran the simulations 50 times, and then he ranked the performance of this 6th method according to different characteristics. So the first one is the mean square of the precision matrix. And in the table, what you see is the average rank. So the smaller is the number, the better is the method, effectively. So you see that if we look at the mean square of the precision matrix, then stars actually did uniformly best. So here, actually, for high dimension, it was always the best one. However, if you look at the mean square of the dissimilarity matrix or the graph correlation, so when you look at second order connectivity on the shared neighbors, then the picture is rather different. So it's interesting for small n, BIC actually did quite well. But for once n is a bit larger, that augmented mean square, where we start with a sort of clustering method and then adjust for possible connections for that, does best. Well, except the other method we suggested, the path connectivity, is better in some cases. And actually, I think the path connectivity tends to be almost reliably second. I think not always, but most of the time. And then what Andrea did, he looked at the discovery rate. So it's the ratio of the true positives among all the genes selected as positives. And what he's, I don't know if you can see. So you can see in some cases, and this is plotted as a function of n. So you see in some cases the true discovery rate increases for larger n, and for some actually decreases. So it decreases for BIC and AIC, so the blue line, you see it's actually going down. Whereas for the two methods we proposed, and Agnes I think as well, the clustering, it actually, it does go, well actually maybe for large p, but certainly for the mean square error method, it certainly goes up or stay constant. And of course, what the methods sort of are really the same, and what we do is select the regularization parameter. So if we look at the ROC curve, you can see the order of the methods. So effectively, this path connectivity analysis, path connectivity method chooses the smallest lambda, so we have the smallest true positives, and then it's followed by, sorry, it's old notation, the augmented mean square error, then by sorry, this is mean square, this is the Agnes method, and then the stars sort of at the end. So that's fairly consistent. And to summarize at least this approach, so this, we just use the clustering method to choose the original estimator, and then the augmented mean square error actually did really well. We think it is one of the, well, among the ones we considered, it seems to be the best method. However, it's quite intensive because it uses subsampling. And the path connectivity does sort of marginally worse, but it's much faster. And of course, the choice of the method sort of here strongly depends on the relative cost of false positive to that of true positive. So if you want to choose lots of true positive, regardless how many false positive you have, you might not want to choose any of the methods. And I'll just talk very briefly about the motivating data. So it's a tumor study. There's quite a small sample size. Andrea actually is analyzing a larger data set, about 130, but it's still relatively small. So he reduced the original number of genes from 25 to about 7,500 without sort of randomly removing uninteresting genes. And then he used the two methods. There are two groups there, sort of healthy and in the tumor. So he actually produced, I don't know if it's several clusters in the graph, and then in actually what he was interested, well, what we were interested in is to look at the different sort of more differential graph, but that's sort of the work we are completing now, and hopefully I'll talk about it in August. And there are some interesting sort of biological discoveries. I think some of them were confirming the previous discoveries in the original data analysis, but some are new. Thanks. Well, this is pretty much the last slide. Just to say that there are packages available for all those methods, so I think it's, and the paper sort of going through the second stage of the revision, so it's on archive at the moment. And then what I'm particularly curious is now to see the consistency properties of the estimate and what sort of we can say about whether we can discover graph or not. with these methods. So particularly this in the previous workshop gave me a lot of reference points for that. Of course, there are other risk functions one can use, and the two current bits of work we are completing now is to test for the difference. So if we have two groups of two conditions, effectively tumor and sample, have two networks, what is the difference? And to whether there is a difference, and if there is, to construct a differential network. So, and these are the references. Thank you very much.
Questions?
So you start out with the graphical assume as a starting point.
Yes.
And so people are twiddling with that one as well. Not using the L1 norm, but using possibly other matrix norms. Have you looked into that at all?
Yes, I remember that in normal lasso, the elastic net seemed to do better, right? With the combination of the L1 and the square root of the L2 norm, effectively. So no, haven't looked at that. I think we were using that. I think lasso does well as a variable selection, right? So that's what we were trying to do. But thank you. I will have a look at that too. Thanks.
When you look at differential networks, then mistakes in terms of missing edges become important as well.
So yeah, what we're interested in, what Andrea is sort of finishing now, is sort of looking at the sparse networks in each condition, but also sparse difference between conditions. I think there was sort of nice work in Bayesian setting for that by Peter Müller, but I think at least in Edinburgh he showed the network of about 10 genes, so we have a little bit more than that. So I think we can handle sort of larger data sets. And also in our setting, we have paired genes, so it's the tissues are taken from the same person just from the normal tissue and the tumor tissue, so it's easier to compare the means. But of course, for the covariance matrix, it's harder. So that's what we are looking at.
Right. Thanks very much.